In this video, we're going to be discussing Gaussian elimination, which is an approach for solving systems of linear equations. And as a motivation, we're going to start out with looking at two simple systems of linear equations in variables x and y, just simply named here system 1 in blue, system 2 in green. And so looking at them, what we should see is that for one of them, solution seems to be a bit more obvious. System 2, we have one variable in the second equation, and so we could simply solve for x and then plug that value for x into the other equation to find a value for y. Interestingly, these two systems have the same solution. X equals 2, y equals 1, even though one of them seems to have a more obvious solution. And so Gaussian elimination provides us with tools that allow us to transform one system of equations into another that is simpler in its form and easier to find its solution, but is guaranteed to have the same solution as the original system of equations. As our first kind of motivation, I want to show you how we could transform system 1 into system 2 with some simple manipulations. And so what we're going to start out by doing is we're going to take and rewrite the first equation in system 1. Here what we see is we have 4x plus y minus 9 equals 0. Since 4x plus y minus 9 equals 0, we can simply add that to any other equation without actually affecting the values on either side of the equal sign. And so what we'll do here is we're going to add 4x plus y minus 9 to the second equation to get 3x minus y plus 4x plus y minus 9 equals 5. So we simply took 4x plus y minus 9 and put it there on the left-hand side of that second equation. In simplifying this, what we should find is that 7x, so 3x plus 4x, the y's cancel out, and the 9 can be moved to the other side, so 7x equals 14. Which is the second equation of system 2. So now we can see how we could transform system 1 into system 2. From here, it's quite easy to find that the solution is x equals 2, y equals 1. So simplifying 7x equals 14, we find that x equals 2. And then we can plug that into the first equation. So we have 4 times 2 plus y equals 9, y equals 1. So what we're going to do in this video is formalize this approach in terms of matrices so that we have an approach for solving systems of equations of arbitrary size. So the first thing that we need to do to be able to formalize this approach of simplifying a system of equations to another form that has a more obvious solution is describe how we actually can represent a system of equations using matrices. And so in matrix form, we can represent a system of equations as some matrix A times u, which is a column vector of unknowns, equals b being the right-hand side. So for our example here, what we see is that we have a coefficient matrix A. Since we have 3 unknowns, the coefficient matrix is going to be a 3 by 3 matrix. Then we have our column vector of unknowns for x, y, and z, and then b. And filling in the coefficient matrix, we simply look at the coefficients in front of each of the unknowns. So each column represents an unknown. The first column is going to be x, then y, and then z, and then the rows represent the different equations. The first row, we have 1, 1, negative 2. For the second row, we have 1, 0, 2. And for the last row, we have 2, 1, 1. And then for filling in b, we simply look at the right-hand side, and so it's just going to be negative 6, 8, and 5. So what we have is a matrix representation of the same system of equations that we will now use to find a solution to the system of equations. So the next thing that we need, now that we have a matrix representation of our system of equations, is rules or guidelines and what type of manipulations we can make on a system of equations or on the matrices that represent them, and still ensure that the systems that we are generating have the same solutions as the original system. And so for that to be true, we have to use what are referred to as linear transformations, which include we can swap any row within the matrix with another, or swap the order of the equations. We can take an equation and have both sides of the equation being multiplied by a non-zero constant, which is equivalent to multiplying the equation by 1. Or we can replace an equation by the sum of itself and a multiple of another, which is equivalent to adding 0 to the equation, similar to what we did in our motivating example. The basic description of Gaussian elimination is that we're going to use linear transformations to convert from one system of equations to another simpler system with a more obvious solution, but that is guaranteed to still have the same set of solutions as the original system. And so in applying Gaussian elimination, we first start with our system of equations. We need to generate the matrix version of these equations, but in performing Gaussian elimination, we often use what's referred to as an augmented matrix in order to provide an even more compact representation. In this augmented matrix, we have our coefficient matrix A, as well as our right-hand side B, all combined in one matrix with a line being there just as a placeholder. So we have a 3x3 matrix, we add an extra column, and so the actual matrix that we're going to be manipulating here is 3 rows by 4 columns. And what we're going to be trying to do with this augmented matrix is transform this system into a simpler system with a more obvious solution. So here we have an identity matrix, which basically means the first equation we have on the left-hand side, x, then y, and then z. And so we simply, from this form, know that x equals 2, y equals -2, z equals 3. And so what we're going to now do is show you the manipulations that we can perform of the original equations here on the left in order to generate a simpler version of the set of equations with a more obvious solution. Gaussian elimination uses these linear transformations that will ensure that our new system will have the same set of solutions as the initial one. But in order to do this in a more efficient manner, it prescribes a way at which we're going to try to convert our initial system to the identity matrix, which is that simplest version of the matrix that we were looking for. And so what's described here is that we're going to first eliminate all non-zero elements below the diagonal, starting in the top left, moving to the bottom right. And then removing those in the above the diagonal, starting in the bottom right, moving to the top left. And for clarity here, let's go ahead and draw the diagonal. So this is what we were referring to as the diagonal. So we're first going to perform manipulations that one by one remove those below the diagonal, starting on the left, moving right, and then those above the diagonal, starting on the right, moving up and to the left. And so our first step here is going to be to remove the 1 in the position of the second row, first column there. And then to do this, we're going to use the row above it, meaning we're going to use the first row. So we're going to have a manipulation of the first row that is focused on only, at this point, removing the first non-zero element in that second row, which is also a 1. And so the operation that can perform this for us is we take the second row and subtract from it the first row, which should produce 0, -1, 4. And then on the right-hand side, the b value in this case becomes 14. So at this point, we've removed the first non-zero element below the diagonal. We're going to continue working our way down the first column to also remove the non-zero element of 2, so the first column of the third row. And so here we're going to, again, use the first row to eliminate that non-zero element now in the third row. The operation that can achieve this is going to be subtracting from the third row 2 times the first row, since we have a value of 2 in the position that we're trying to eliminate. This will result in the third row having values of 0, -1, 5, and 17. We have one non-zero element remaining below the diagonal. This is -1 here. But at this point, we now transition to using the second row to manipulate the third row as we have moved to a different column. And so in this case, we can now take the third row and subtract from it the second row, which should now give us values of 0, 0, 1, and 3. That's simply by taking -1 minus 1, 5 minus 4, 17 minus 14 to find out that our new third row of our augmented matrix will be 0, 0, 1, 3, which implies that the value of z, our third unknown, will be 3. From this, we could easily work our way back to find the values of x and y, but we could also do as described to ultimately end up with the identity matrix, where we need to do some further manipulations and remove the non-zero elements above the diagonal by working kind of in the opposite direction. So now we're going to start with using the third row to manipulate the second row, working up that third column, and then using the second row again to work on the first row in order to ultimately remove all the non-zero elements above the diagonal. And so here we can see the series of manipulations that would achieve that. We ultimately want to have an identity matrix which has 1s down the diagonal, so we need to get rid of the -1 in the position to 2. And then from there, we can take the second row and add to it 4 times row 3. Following that, we'll take the first row and add 2 times R3. And then ultimately take the first row and subtract from it the second row so that we can get to the final form, which is going to be that we saw before, where we have 1, 0, 0, 0, 1, 0, 0, 0, 1, 2, -2, 3, which again defines that x equals 2, y equals -2, and z equals 3. This concludes our video on Gaussian elimination. Future videos will be aimed at other uses of Gaussian elimination as well as other approaches for solving systems of linear equations.